Hi, my name is Stan Forster. I'm your instructor for NS130. I hope you enjoyed the video I made for you earlier about navigating the H-hard diagram and the kinds of information that it can tell you. Excuse that. Okay, so we're going to continue with our study of the lives of stars, and it might be informative at this point to ask, how do we know what we know? And it's a combination of the overlap of many sciences. Okay, for instance, mathematics and statistics. We're going to bring physics in, nuclear physics and astrophysics, which are not entirely unrelated. Observational astronomy, which is going to gather that direct evidence from the universe. Okay, so um, let's talk about how do we investigate some of these things. And one of the tools early on, when we didn't actually know how far away the stars were, was we would look at binary pairs, binary stars. And because binary stars were associated with them, they'd orbit around each other, um, we could tell that they were about the same distance. Okay, and so given a spectral class, we knew what the temperature was. We didn't quite know how far away they were, but we could compare the size and the luminosity of two different spectral classes at the same distance, and then from that we can infer many things that led to the development of the HR diagram. Now, later on you're going to study something about parallax, where we actually make a direct measurement of how far away these stars are, and these are very, very sensitive measurements that you have to make. And it deals with, like, for instance, if you put your thumb up and you over one eye, right, and then you close the other eye, okay, all of a sudden it seems like the thumb moves, right, and that's because the distance between your eyes, that when you're using one eye and then you close the other eye, okay, and it seems something in the foreground seems to shift position against the distant background, and the very most distant objects out there would be quasars and distant galaxies. But so the nearby stars, we could figure out where they were, or at least how far they were, with some precision. Now, that was done from the ground using optical telescopes and later on cameras. But since then, we've had two space missions. The first was Hipparcos. That was back when I was a student. And they measured many of the most nearby stars, and we got a much better picture of how big our galaxy was and how far things away were. The ESA, the European Space Agency, put up Gaia, and I believe it's still up there. You can check on that and correct me if I'm wrong. But they measured stars that are in the most visible stars in the most distant portions of our visible galaxy. If you look at the data in the map, there's this great big gaping hole in the data, and that's toward the center of our galaxy because it's so dense that we obviously can't see beyond that. Okay, it's like without a mirror trying to draw the back of your head, so we can't really look over there to get data. But that has given us direct measurements of the distances to these things, and then we can use the 1 over r squared law to figure out, okay, so the luminosity drops by this much, or excuse me, the luminosity doesn't drop, but the brightness drops with distance, and we can compare all those models, and slowly, surely, measurement by measurement, correction by correction, we build up a picture of how the galaxy is put together and how stellar populations are put together. Like, for instance, those very distant measurements. One of the things that they found was that the data didn't match what we expected. And then somebody said, "Oh, wait a minute. Maybe there's interstellar dust in the way, and that's changing the spectrum slightly." And it does. So the blue gets preferentially scattered, and you're left with mostly longer wavelength stuff, and red portions of the spectrum when it comes to you, and so the spectrum doesn't look quite right, But then they said, okay, well, for every parsec they're going to go through so much dust, and oh, hey, look at that, the error bars on the the things where he said, well, this doesn't quite match, and suddenly they're a little bit closer together. They make a little bit more sense, and then people made corrections for relative motion and all sorts of things, and that's what scientists do. They look at the data and they say, okay, well, how can we make this better? What have we not accounted for? And it's an iterative process. It's you make observations, and where the observations don't match the theory, the observations aren't wrong. What you look out there, see out there in the universe, that's what's there. It's your theory that you need to take a look at. Maybe it needs to be tweaked a little bit. Okay, in the case of a correction for interstellar dust, or let's look back at physics back at the early 1900s. They had to completely abandon their idea of this ether through which the medium through which they thought light traveled, and had to be replaced by a completely different theory. And that theory gave us special and general relativity. But yeah, so that's just a quick overview. Just pay attention to how we know what we know, and let's have fun. Okay.